Hello, Dan here from howtomechatronics.com, and in this video we will learn what's better, a 3D printed cycloidal drive, a planetary gearbox or a belt drive. We'll compare them in several categories, measure their efficiency or torque output, measure their accuracy or backlash, and see how durable they are. Also, we will compare them in terms of cost, size, weight and how easy they are to be made. Why this comparison? Well, the main goal will be to understand which drive or speed reducer would be a better choice for a robot joint. In the following period, I will be designing and making some robotic arms, so with these comparison results, I, and ultimately you, will be able to choose what drive or speed reducer would work best for your robot design. I already have dedicated videos on my channel explaining in details what are and how cycloidal drive and planetary gearbox work, as well as how to design them, so I would suggest checking those videos out for more details. Here in this video, we will just take a look at the key input parameters that define the design of the drives. I will start with the cycloidal drive. When designing a cycloidal drive, the main input parameters are the reduction ratio that we want to achieve, of course, and the type or the size of the rollers that we will use. For this build, as rollers, I decided to use bushings with 6mm inner and 10mm outer diameter. These bushings are much smoother than the bushings that I used in my previous builds with 8mm outer diameter, so I wanted to see if I can get better performance of the cycloidal drive with them. Though these 10mm bushings come at a price, as the roller's size directly defines the size of the cycloidal disc and the whole drive. Now I will show you how I easily designed the cycloidal drive using Onshape, which is also the sponsor of this video. Onshape is a professional grade CAD and PDM system for businesses. Onshape is built entirely in the cloud and works in a browser, which allows for some really unique features like it enables secure real-time collaboration, multiple people can access and edit a design at the same time. It runs on any device and you don't need an IT team to implement or update. It tracks all changes and has infinite restore capabilities. You can branch and merge design changes similar to Git. Unlike other CAD software, Onshape never crashes and never loses your data. These things allow companies to move quickly and focus on their products rather than managing their CAD system. For viewers in the US, Onshape just announced Onshape Government, which runs on AWS GovCloud and allows companies who require regulatory compliance like ITAR and EAR to use Onshape. I highly encourage engineers to sign up for Onshape and get up to 6 months of the professional version for free at onshape.pro/howtomechatronics. Back to topic, it's quite easy to generate the cycloidal discs with the help of the custom-built cycloidal drive feature script library in Onshape. We just have to enter our parameters: the tooth number of the disc, the eccentricity, and the rollers or pins diameters, both the outer pins or ring gear rollers and the inner pins or the output shaft rollers. As we enter these values, the 3D model updates, as well as the other parameters, which we should keep track of and correct them later if needed. The circle diameter is the overall dimension of the disc, and the goal is to be as small as possible according to our fixed input parameters, the number of pins or their dimensions. The cycloidal disc is the most important part of the drive, and the rest of the parts are designed around it. Of course, there are many other input parameters that contribute the overall design of the drive, such as the motor type, how we would like to drive the input shaft, what kind of bearings we have available to work with, the application of the gearbox itself, and so on. Nevertheless, now let's take a look at the planetary gearbox. This is actually the same design from my previous video, where I talked in details how to design a planetary gearbox. It's a 2-stage planetary gearbox with 4:1 reduction on each stage for a total of 16:1 reduction ratio. For better performance, instead of bushings, here I'm using ball bearings for the planet gears. Each planet gear accommodates 2 ball bearings, so we can easily lock the gear in place and accept axial forces that occur since the gears are helical. Next, we can take a look at the belt drive design. Here we also want the same reduction ratio of 16:1, and we can easily make that in 2 stages with 4:1 ratio. I chose to use a GT2 belt because it's the most popular belt and it offers great performance in terms of backlash. Almost all 3D printers use this type of belts. I got two 226mm closed loop GT2 belts with 10mm width. Now for these belts to work we need suitable GT2 pulleys. Again, using a custom built feature script library in Onshape, we can easily generate the GT2 pulleys. Here we just have to select the type of the GT2 belt, whether it's 3 or 2mm each, and enter the number of teeth the pulley will have. I set the input pulley to have 20 teeth and the output pulley 80 teeth. The first stage output pulley with 80 teeth is the input pulley with 20 teeth for the second stage, and it sits on 2 ball bearings. The shaft for it is a 6mm 3D printed shaft with M4 bolt that goes through it for making it stronger. The second stage output pulley is supported with 2 ball bearings, one at the motor input shaft and the other at the housing. I used the Creality K2 Plus 3D printer for printing all of the 3D printed parts. When 3D printing, it's essential to use the horizontal expansion feature, or now in the new Creality print slicer that I use, it's called XY contour compensation and XY hole compensation. If we leave these settings by default, the print's dimensions probably won't come out exactly the same as in the CAD model, and that's due to the expansion of the filament when 3D printing. The holes usually come out smaller and the contours bigger. Now, what value to use for these two settings is the key question, because they directly affect the precision or the performance of the drives that we are making. I actually use different values for each part depending on the purpose of the part. For example, when 3D printing the cycloidal discs, I used value of 0.12mm for the XY hole compensation and minus 0.15mm for the contour. In that way, I got the holes where the output rollers go at the right dimension, as well as the contour of the disc, which needed to be a bit smaller in order to fit in the ring gear rollers. I made a list of all values that I used for each part. You can try these values when 3D printing, but you might need different values depending on your 3D printer. You can only get these values right by doing some test prints with different values. You will later see in the comparison tests how adjusting these values affect the performance of the drives. By the way, here I would like to give a shout out to Creality for providing me this excellent 3D printer. The Creality K2 Plus is actually one of the best 3D printers I have ever used. It's capable of doing anything you would ever need from a 3D printer. It has outstanding print quality, it's fast, it can print any material with ease, it can print multicolor, and it has a ton of cool and practical features. The Creality filament system unit that comes with the 3D printer is also amazing, because you can load up to 4 different filaments in it and have them ready to be used at any time. You don't have to waste time changing filaments. Plus, changing the filaments is also a breeze. You just pull out the old one and insert the new one, and the machine does the rest of the job. So this unit is very practical even if you don't need multicolor printing. You can check out the K2 Plus on the Creality website stores. The links are in the description of the video. Okay, so here are all of the 3D printed parts and the other components needed for assembling the 3-speed reducers. As we can notice, the belt drive has the fewest number of parts, and on the other hand, for the cycloidal drive we need considerably more components like the pins and the bushings. The Planetary gearbox is somewhere in the middle for that matter. You can find a complete list of all components needed for these drives, like the bushings, the belts, the bearings and the bolts and nuts on the website article. The link to it is in the video description. Now I will quickly walk you through the assembly process of these drives. For assembling the belt drive, first we need to insert the final output pulley in place through the ball bearing at the housing. Then we need to install the ball bearing inside the output pulley, where the first input pulley will go. This input pulley first needs to be secured to the stepper motor, and for that purpose I made 2 slots for inserting M3 nuts, and then using M3 grab screws we can firmly secure the pulley in place. The pulley should stay 2 mm above the stepper motor. Before inserting the stepper, we need to insert the 2 belts. Then we can secure the stepper to the housing using some M3 bolts. As I wanted the drive to be as compact as possible, securing these bolts was only possible with some narrow pliers. Not convenient at all, but the goal was also the drive to be as sturdy as possible to get the best performance out of it. Next we can insert the intermediate pulley and wrap the 2 belts around it. The pulley will accommodate 2 ball bearings with a small distance ring in between them. Then we can insert the shaft for the pulley. It's a 3D printed hollow 6 mm shaft that will be reinforced with an M3 bolt. Here, for example, we can just use an M6 bolt instead of this, but in that way we won't have that tight connection because the M6 bolt outer diameter is about 5.8 mm, and with the 3D printed shaft we can make it exactly 6 mm or 5.95 mm to perfectly fit through the bearings. At the bottom side we need to insert a distance ring on which the ball bearing will sit. Then we can stretch the belts and insert the shaft all the way through the bearings and into the other side of the housing. Then we can insert the M4 bolt through it and secure everything in place with an M4 nut. And that's it. The belts are fairly tight, but for better control and performance we should add tensioners to them. I made the belt tensioners with the help of a ball bearing with 13 mm outer diameter that is attached on a small bracket with some M3 bolts and nuts. We can push this bracket against the belt to tension it and then tighten the bolt. It's a rather simple mechanism that works just right. Lastly, we can secure the cover of the drive with some M3 bolts and nuts in it and add threaded inserts to the output shaft for attaching stuff to it. That's it. Now let's take a look at the cycloidal drive build. As I mentioned, I already have detailed videos how to build a cycloidal drive and a planetary gearbox, so here I will just say a few words about them. When assembling the cycloidal drive, I came to a problem that I couldn't insert the second disc in place, although I was following all the rules, placed it 180 degrees out of phase and double checked all dimensions. But then I realized that the problem was the reduction ratio. A cycloidal drive must have an odd number of ratio in order to work properly. In my previous videos I have already made 3 different designs of cycloidal drives, but their reduction ratio was an odd number by chance, so I have missed the fact that in order to make a cycloidal drive that will work with 2 cycloidal discs, you must have an odd number of teeth or lobes on the discs. That also meant that we need odd number of reduction ratio. So I changed the number of teeth to 15 and the number of ring gear rollers to 16 and reprinted the housing and the discs. Now with this reduction ratio, I was able to install the 2 cycloidal discs properly and finish the whole assembly. As for the planetary gearbox, the assembly is pretty simple and fast. First goes the sun gear into the stepper motor, then the stepper motor to the housing. Next, we need to assemble the first stage carrier with the planetary gears on it. I made the carrier as a single print in this case, in order to be sturdier and more precise, though we need to use supports when 3D printing them. Next, we can insert the first stage subassembly into the housing, which is actually the ring gear of the planetary gearbox. Now, depending how accurate the prints are, the teeth meshing can be either tight or loose. In this case here I used a value of -0.15 mm horizontal expansion when 3D printing the ring gear and -0.05 mm for the planet gears. As we can notice, that resulted in a looser fit between the ring gear and the planet gears. When inserted all the way in, with the input sun gear also meshed with the planet gears, the wobble is reduced but still exists. I also tried printing the housing with values of -0.1, -0.05 and 0 mm for the horizontal expansion feature to see how that will affect the output performance that we will get from the gearbox. We will see that later in the tests. Alright, so here I have the 3 drives ready, and now we can take a look at the comparison tests. I will start with testing their accuracy or the backlash. Here's the Planetary gearbox first. Here I'm testing its repeatability, and it shows good results. The bar gets in place within 1/100th of a millimeter at a distance of 20 centimeters. But of course, when applied a force to it, the backlash gets noticeable. The bar plays couple of millimeters up and down at that distance. When moving it by hand, it feels like there is a free play on the output without any resistance. To express the backlash in its typical unit, arc minutes, we need to do the following. We should measure the displacement in both directions, while applying a load of around 1 to 2% of the nominal torque capabilities of the gearbox. When testing the torque of the gearbox, I got a maximum reading of around 32 newtons at a distance of 10 centimeters. So I guess for testing the backlash, we should apply a load of around 0.5 newtons, but let's make it 2 newtons at a distance of 20 centimeters. With this load, I got a displacement of around 2.9 mm in one direction and 0.75 mm in the other direction. To express this measurement in backlash unit, arc minutes, we need to calculate the angle of displacement alpha. We do that with the help of some simple trigonometry, and the angle comes out to be around 1 degree. 1 arc minute is 1/116th of a degree, so the backlash of this 3D printed Planetary gearbox is around 16 arc minutes. Please let me know in the comments if you know whether that's the right way to take the measurements and calculate the backlash. Even if it's not 100% correct, we will use the same method to express the backlash for each drive, so that at the end we will have comparable results. Now, as I mentioned earlier, depending on how tight or loose the meshing of the teeth is, the gearbox should provide different results. And here's a confirmation of that. In the first test, the gearbox ring gear was printed with horizontal expansion of -0.15 mm and the Planetary gears with -0.05 mm. Now I replaced the ring gear with horizontal expansion of 0 mm, which made a tighter fit. Now the gearbox showed a backlash of around 50 arc minutes. That's like 50% better result, and it could be even felt by hand that the gearbox has now less play. To further improve the backlash, I printed the Planetary gears also with 0 horizontal expansion, and again I got better results, around 30 arc minutes of backlash. So from the initial 60 arc minutes, we improved the backlash of the gearbox to around 30 arc minutes. Please note though that in the design process itself, when generating the gears with the custom feature script in Onshape, I added a backlash or offset of 0.1 mm to the gears. So therefore I can print them all with 0 mm horizontal expansion and still be able to assemble them properly and get good results. That means we can even further increase the backlash by removing that 0.1 mm offset when generating the gears, but I believe that if we do that, we won't be able to assemble the gears at all, or maybe we will be able to put them together, but they will lose efficiency or even jam completely. We will see that behavior in a bit in the efficiency or torque tests. Nevertheless, now let's take a look at the cycloidal drive backlash. In terms of repeatability, it showed worse results. The bar was getting back at various points within 1/110th of a millimeter. As for the backlash, I calculated a value of around 60 arc minutes. That's the same like in the worst case with the Planetary gearbox. Though here, when moving it by hand, it didn't feel like there is any free play, but there was some resistance right away. For this test, the cycloidal discs were printed with -0.15 mm horizontal expansion, and when assembling they were actually quite tight. So I tried printing them with -0.2 mm horizontal expansion and plus 0.2 mm hole horizontal expansion, because the precision of the 6 output holes in the cycloidal disc also contribute to the performance of the drive. So with the looser fit of the discs, the results were way worse, around 150 arc minutes, and there was a lot of free play on the shaft when moving it by hand. Next, let's take a look how the belt drive performed. The repeatability seems to be quite good, within 1/100th of a millimeter at a distance of 20 centimeters. But we can also notice that there is like an overshoot. The bar goes up to 0.04 millimeters and gets back to 0.03 millimeters. When testing the backlash, I calculated a value of around 45 arc minutes. That's a good result compared to the other two drives. But here with the belt drive, I also have the possibility to control the tension of the belt and with that maybe improve the backlash. So here I did tension the belt a bit more and now the backlash was reduced to around 25 arc minutes. So the belt drive gave the best result out of the three drives in terms of backlash. Now let's compare their efficiency or torque output. I will start with the cycloidal drive. At a distance of 10 centimeters, I got a reading of around 60 newtons, or that's a torque of around 160 newton centimeters. Compared to the torque of the stepper motor showed without the drive, around 18 newton centimeters, that's a torque increase of around 9 times. That's a low efficiency of the drive of just around 60%. The reduction ratio of this drive is 15:1, and in ideal condition we should get 15 times torque increase, but we got only around 60% of that. That's so because I guess there is a lot of friction going on in the drive, or high resistance, as the cycloidal discs fit quite tight. If we compare that with the cycloidal discs that had looser fit, I got a reading of around 18 newtons, or 180 newton centimeters. That's like 10% better efficiency, but still not great, only around 66% efficiency. Let's take a look at the Planetary gearbox efficiency now. At a distance of 10 centimeters I got a reading of around 36 newtons, or that's a torque of around 350 newton centimeters. I was kind of surprised by these results, because compared to the torque of the stepper motor showed without the drive, in this case around 22 newton centimeters, that's a torque increase of around 15 times. This gearbox has a reduction ratio of 16:1, so that's around 90 to 95% efficiency. Though this test was made with the gears with looser fit, where there was a small play of the shaft when moving it by hand. But here are the two other cases that I tested with tighter fits of the gears meshing. I got around 310 newton centimeters torque output with the ring gear 3D printed with 0 mm horizontal expansion, or that's around 84% efficiency. And even with the tighter fit of the gears, with all Planetary gears printed with 0 mm horizontal expansion, around 290 newton centimeters torque output, or that's 78% efficiency. Still a very good result for a 3D printed gearbox. Lastly, let's take a look at the belt drive efficiency. In this first test, with the belts being a bit looser, I got a reading of around 260 newton centimeters of torque, which is efficiency of around 70%, as the stepper motor had a torque of around 23 newton centimeters without the drive. However, in this case, the problem was that the belt was keeping at the second stage smaller input pulley, instead of the stepper motor itself. With the belts tensioned better, the output torque increased to around 360 newton centimeters, or that's efficiency of around 95 to 97%. That's really impressive. The belt drive came out to be the most efficient drive, as well as the best performer in terms of backlash. But before we make a conclusion which 3D printed drive is the best, let's take a look at few more comparisons. I tried to do a durability test by running the drives for a longer period of time with some weight on them. I used some DC motors as weight and made the drives rotate with a sudden change in the direction of the rotation in order to add more stress to them. After around 2 hours, the cycloidal drive failed. It couldn't move the load anymore. The belt drive and the Planetary gearbox continued for 8 more hours with the same movements, and they were just fine. After the durability test, I tested again their backlash. The cycloidal drive totally lost its precision. There was like 10 mm free play at a distance of 20 centimeters. The Planetary gearbox also introduced free play on the output shaft, which previously didn't exist. I was using the gears with the tightest fit for this durability test. In backlash unit, it went from around 30 arc minutes before the test to 16 arc minutes after the test. And the belt drive, after the durability test, it showed a backlash of around 35 arc minutes, and before the test there was around 25 arc minutes of backlash. I opened the drives to see what has been going on inside and to see what causes this reduction in the precision of the drives. In the cycloidal drive there were significant marks of wear of the cycloidal discs, both on the cycloidal disc profile and the output holes of the discs. So as the PLA discs deformed, they have reduced the precision of the drive significantly. On the Planetary gearbox, I couldn't notice much wear or deformations on the gears. There is probably some very small deformations or wear, maybe a wear of the seams that appear when 3D printing them. So once that seams wear out, the backlash increases. Maybe if we print the gears with even smaller tolerances or make them fit tighter at the beginning, even at the cost of losing some efficiency, but after the initial wear out, they will get the right efficiency and precision. As for the belt drive, we can notice that there is a wear on the back side of the belt where the tensioner bearing pushes the belt, though this problem can be easily solved by using a proper 10mm idler wheel. Also, we can always add more tension to the belts even after some use to improve the precision. With the other two drives, there is nothing we can do to improve the precision. So, considering all of this, the belt drive came out as the best performer. And not just that, it also beat the other two drives in terms of weight, cost and how easy it is to be made. The total weight of the belt drive, including the stepper motor, was around 550 grams, the Planetary gearbox around 600 grams and the cycloidal drive around 710 grams. Of course, the weight is very important if we use these drives as robot joints. In terms of size, the cycloidal drive is definitely the most compact drive, while the Planetary gearbox and the belt drive are somewhere similar, but with a bit different configuration. On the other hand, the cycloidal drive is the most complex or difficult to assemble, followed by the Planetary gearbox and the belt drive as the easiest to assemble. That's so because the belt drive actually has the fewest number of components other than the 3D printed parts. This also directly affects the cost of building the drive. The cycloidal drive that I built for this video has the most components other than the 3D printed parts, pins, bushings and bearings, and it costs around $28 to build, not including the 3D printed parts. Then we have the Planetary gearbox that costs around $23, and lastly the belt drive that costs only quarter or 1/3 of that, or around $7.8. So considering all of this, what's my final verdict? What's better, a 3D printed cycloidal drive, a Planetary gearbox or a belt drive? Well, I would definitely avoid the cycloidal drive, as the only category that was better than the other drives was in its size or compactness. On the other hand, the Planetary gearbox and the belt drive showed very similar performance, but if I must pick up a winner from all the tests that I made, that must be the belt drive. It performed the best in every category: precision, efficiency and durability, as well as it was the easiest and cheapest to build. However, I won't leave this test here, but actually I will make further test comparisons between the Planetary gearbox and the belt drive in real scenarios. Or I will build two robot arms, one employing 3D printed Planetary gearboxes and the other employing 3D printed belt drives, and then we will see how they will perform in real situation. I hope you liked this video and learned something new. Don't forget to subscribe, and for more tutorials and projects, visit howtomechatronics.com.